Hello. So in this lecture, we're going to talk about big O notation or asymptotic notation, which is an alternative to trying to accurately compute or count the number of computer steps. So the idea here is that if an algorithm has an input of size n, and we'll talk a little bit more about input sizes later, but think here about the number of bits needed to encode the input. Then we just report the runtime as it's scaling in terms of n. So to give an example, let's say if runtime is 10n cubed plus 7n, we drop the constants. And 2, we drop the lower order terms. And from that, we get big O of n cubed. Now, that's kind of the informal way that we do this. More formally, big O notation can be defined as follows. So let me say big O notation. And let's say I have two functions, f of n and g of n. They're each functions from the positive integers. So positive integers here is denoted this script n, like that. And positive reals is this kind of script r. So they map from the positive integers to the positive reals. Then we say that f is big O of g if there exists a constant n, so a big enough number n, and another constant c, such that f is smaller than that constant times g, as long as n is bigger than our capital N. So when we go far enough out, I guess, on the n axis, f is eventually below g. But instead of saying it's below g, we say it's below a constant times g. So it can actually be above, but it can't be growing faster, right? So equivalently, f of n is in big O of g of n if the ratio of f of n over g of n. Remember, according to this kind of g of n is at least as big as f of n up to a constant. So if this is bounded above as n goes to infinity. And so this is how we upper bound the runtime of an algorithm. We can also lower bound the runtime of an algorithm. Say an algorithm runs at least, the runtime takes at least this much. And so to do that, we use a big omega notation. And the definition is similar. So it says f is in big omega of g if there exists a number n and another constant c, such that f is bigger than the constant times g for all n bigger than this capital N. So that means that, if we make n big enough, f is growing at least as fast as g. And so an equivalent definition is that this ratio of f over g is bounded from below as n goes to infinity. Right? The numerator is growing at least as fast as the denominator. So just as a simple example, we say, let's say f of n is 100n and g of n is n squared. Then as n becomes big, g starts to beat out f, right? In particular, when n gets bigger than 100, we see that it's going to be, this one will always be 100 times n. And this one, for example, when n is 101, it's going to be 101 times 101. So g will eventually beat out f. And so this means that f is upper bounded. So f of n, first of all, is big O of n. We also have g of n is big O of n squared. And the two functions look something like this. Where f of n is just a straight line. And g of n is a parabola, right? So this is g of n. This is f of n. And so eventually, right? I mean, there's a period in time where f is larger than g, but eventually f becomes, or g becomes larger than f. And so we would say here we have that f is in big O of g, but g is not in big O of f. Right? When we become large enough, like over here, when n becomes large enough, g lies above f. So g is an upper bound to f. The one other notation is big theta notation. And so maybe I'll just write this here. If f of n is equal to big O of g of n, and f of n is equal to big omega of g of n, then we say f of n is equal to big theta. This is like an uppercase theta of g of n. And just one like thing here, when I say that f is in big omega of g, that's the same thing as saying that g of n is equal to big O of f of n. Right, if one lower bounds the other, if f, so this says g lower bounds f, that means that f upper bounds g, and so on. Okay, so to give an analogy, f is big O of g is kind of like saying that f is less than or equal to g. I mean, it's not quite because you have this constant multiplying in front. If f is in big omega of g, that's kind of similar to saying that f is bigger than g. And if f is equal to big theta of g, that's similar to saying that f is equal to g. So the first one, f grows faster than g. The second one, first one, f grows no faster than g. The second one, f grows at least as fast as g. And the third one, f and g grow at the same rate. So let me give you one more example. Let's say that f of n is equal to 2 to the power of n. And let's say that g of n is equal to 2 to the power of n plus 1. So what do we know immediately by looking at this? Well, G is bigger than F, right? So first, we know that F is equal to big O of G, right? G upper bounds F. But also, we know that G can just be written as 2 times 2 to the power of n, right? Because it's 2 to the power of n plus 1, which is just a constant times 2 to the power of n, which is big O of 2 to the n, right? And 2 to the n is f, so this is big O of f. So we have f is big O of g, and we also have that g is big O of f. And that then implies that f is equal to big theta of g. So these two functions grow at the same rate because they differ only by a constant, essentially. Okay. So this is formalizing the idea that I think you already know. The thing that's important is that we have these 3 notations, right? We have big O, big omega, and big theta. Let's now use the definition, just so that we make sure we understand what the definition is saying, to show that 5n squared plus 10n is in big theta of n squared. So first, so to do this, we need to show that there exist these constants c and n that satisfy the definition. So first, let's show that 5n squared plus 10n is in big O of n squared. To do this, show that there exists c, a constant c, and another constant n, such that 5n squared plus 10n is less than or equal to this constant times n squared, as long as n is bigger than or equal to this capital N. So the question is, I have to figure out is, what do I set this c to and what do I set this n to make this hold? One way to deal with an equation like this is to get rid of you can see we have a common n in all of them. So let's just divide by n, or divide by n squared, actually might be even easier. And then I get 5 plus 10 over n has to be less than or equal to c. So how big, what are values of n and c for which this holds? How about I take, let's say that n, I take capital N as 10. Then I know that no matter any lowercase n I plug in has to be at least 10. So this number is at most 1, right? 10 over n is at most 1. That means I have 5 plus 1, that's 6. So that means that c, as long as I make c at least as big as 6, this thing is satisfied. So c is 6. And the inequality so that now we know we've established this part. So now we want to in the end show that it's big theta, right? So we should also show that it's in big omega of n squared, right? So now let's go second. We want to show that 5n squared plus 10n is equal to big omega of n squared, i.e., there exist C and N, which are positive, such that 5n squared plus 10n is greater than or equal to a constant times n squared for all n greater than or equal to n. This one's pretty easy, right? Because the left-hand side is at least as big as 5n squared, and the right-hand side is c times n squared. So what if I just take any value of lowercase n bigger than 1, bigger than or equal to 1, and take c equals to 1. Then we just have that 5n squared plus 10n is greater than or equal to n squared, which is true. Therefore, 5n squared plus 10n is equal to big omega of n squared. And then combine the fact that it's big O and big omega. We have that 5n squared plus 10n is equal to big theta of n squared. Now, the thing to notice, right, is these numbers that I picked here to make the inequalities work are kind of, they're not arbitrary. They have to satisfy, they have to be such that this inequality is satisfied, but there's many sets of numbers for which it's true. We say that F, or like that this is in big O of the right-hand side, as long as we can find a set of numbers, find a C and a capital N for which it's true. It doesn't have to be true for all of them. You and I don't have to come up with the same ones, nothing like that. It's just that we have to be able to find a C and an N for which this inequality holds, and then in the second case, a C and an N for which this inequality holds. And we did it, and so we've established our final result, which is that 5n squared plus 10n is in big theta. So that's all I wanted to cover in this lecture. In the next set of lectures, which will start next week, we'll actually get into things. We'll start looking at algorithms, start analyzing runtime. And so this was just kind of an intro to get us going and to review some of this notation that maybe you've seen but haven't dealt with that recently. So I will see you probably next week. And yeah, have a good day. Bye, everyone.